All right, this is section 5.1 of chapter 5, basic introduction to steel beams. All right, so really so far what we've talked about is columns. All right, so let me change my color here a little. All right, so we've looked at columns, all right, that had a length, an axial load, and we called this length L critical, L sub C. Remember, L sub C was K times L X, L Y, that type of thing, and that gave us our strength. Now we're switching to beams, all right? So now beams are going to be more horizontal. My load's going to be perpendicular to the span. All right, here's my span. So, distinctly different. Similar in that we're going to have what we call unbraced lengths. Okay, we're going to have locations, we're going to have spans. We might have an unbraced length L sub B that's the entire length of the beam. And just as in columns, the longer the unbraced length, the weaker the beam will be. Okay, so similarities to columns, but certainly some differences. Okay. So when we think of a beam, right, and I'm again thinking this as span, L is span. One of the things, again, a rule of thumb is that the span to depth ratio is 12 to 24. Okay, and this depth is in feet. All right, so you're going to take, D divided by 12. Okay, so if I say a W12 by 14, right? A W12 is 1 foot deep. So I would expect this beam to have a span, right, of 12 feet to 24 feet. All right, if I had a W18, my D is 18 divided by 12, 1.5. So there I would have 18 to 27 feet, right? Or I'm sorry, 18 to 36. Okay, 12 to 24. Okay, so, or you could think of the depth as feet, 18 inches deep, 18-foot span. 12 inches deep, 12-foot span. 24 inches deep, 24-foot span. Okay, again, just a rule of thumb, but you have to always go back to our shear, moment, and deflection. All right. In columns, we really didn't talk about deflection at all. The force in the column was axial. Now the force in the beams are going to be shear and moment. Okay, so we're going to really go to chapter F for flexure and chapter G for shear. Okay, and we will dabble in connections. Okay, and that's going to be chapter J, but primarily it's F and G. It's chapters F and chapter G. All right, so again, we think of a beam, I'm thinking uniform load, I'm thinking concentrated load, thinking certainly W shapes, okay, plate girders, built-up girders, composite steel beams, even open web joists. Even though they're primarily a truss, they do support loads that beams do, and they are a big competitor with steel beams. And again, we look at a beam shop drawing, okay, again, from a previous life, these types of things we saw. Pretty simple looking piece of steel, just has some holes in the ends for a connection, but notice the length that's in the span, the size, W12, okay, and the actual length of this beam that they would cut in the shop to start fabricating is going to be 17 foot 11 and 11/16. So that makes me want to say or believe that the actual column to column or beam to beam, girder to girder, whatever this thing's being connected to, most likely another girder because it has this cope, okay, that's a cope. When you cut out the top of the column, that's what we call a cope. So chances are this beam is connecting into a deeper beam or a girder, right? Something like that, and probably has a, you know, a connection like that. Okay, so I would suspect that the center to center of these beams is 18 feet. Okay, or of the girders. If I call this the girder, right, and this is my W12 that we're looking at. Okay, and notice the span to depth. Span to depth ratio here. Again, we said 12 to 24, or if you divide that by 12, it's 1 to 2. But if I take the span, right, is 18, and my depth is W12 divided by 12, and so that means my ratio is 18 divided by 1, so it's about 18, so it's halfway in between. All right, so my span to depth ratio is 18 inches, or 18 for this W12, so it's within our rule of thumb of 12 to 24. Okay, but other things of interest here, certainly you have your beam size, you have the grade of steel. Oops. All right. Interesting here, square area or square feet of the surface, again for painting purposes or cleaning maybe. Okay, but and then certainly the weight for shipping. Okay. Again, has a mark, a specific identifier. So this beam would be marked somehow, maybe sprayed on with stencils and paint, or even today they use inkjet markers that put the beam mark right on the beam once it's painted. In the sequence, you know, that's sort of like how we break up the building. You can't deliver all the steel at once to most sites, so you have to sequence it, and you deliver one sequence, second sequence as the erector needs it. Okay. Again, some highlights here: hole size, typical hole size, total weight, grade of steel. You know, just a bunch of different information that is used to track how this, what goes into paint and what goes into fabricating this beam. Notice here, no paint and SSPC 2, so that's a Structural Steel Painting Council cleaning definition, SP2. Okay, SP2, SP1. SP1 is the most difficult one. It's almost blast clean. So lots of information here. All right. So another one that you'll see often is, you know, steel joist. Okay. Again, steel joist more like a truss. Okay. Couple different methods of fabricating. And again, I don't particularly care for this picture here because, you know, it has this round bar bottom chord. This type of steel joist hasn't been fabricated since 60s or 70s, 1960s, 1970s. Okay, they're more like this with this type of angle. This is what we call, when I say angle web, most likely it's what they call a crimped angle. Okay. And what that means is the ends of the angle are squeezed down. So they look like this to start, but then we crimp it and it just kind of squeezes the end down to 1 inch, okay, or the spacing of the cords. All right, but these things resist loads similar to beams, so they are definitely a competitor to steel beams. All right. And then finally, composite joist or composite beams, right? There's this shear stud. shear studs welded through the metal deck, fastened to the top of the beam. So they place the deck on first, weld the shear stud on second, and place the concrete third. Okay, and once the concrete solidifies, it serves as the compression side of the beam. Real efficient use of material. Okay. So spans are much greater than depth. Again, span to depth ratio is about 12 to 24. Okay. And again, you want to make this depth in feet. All right, the depth is in feet. Okay. Loads are through the shear center, right? Remember, again, here's our XX axis and here's our YY axis. Shear center is right there, so there's no torsion. Loads are definitely perpendicular to the span, right? Here's our span, okay? We don't typically see axial forces for this chapter. This will be chapter 6. And in the AISC, it will be section chapter H. Okay. So again, just to remind you what loading looks like, it looks a lot like what we saw in all through statics and structural analysis, right? Uniform loads per foot, triangular loads, concentrated loads, and notice where this is coming from, a steel joist reference. So the steel joist, again, definitely compete with steel beams. Okay. Again, another important thing for beams is bracing. Okay. So if we think of bracing with the big X, our primary assumption is that the supports are always braced. Okay, and when we say braced in this case, when we think of a brace point for a beam, it's going to prevent that beam from displacing laterally, right, going left or right. That can't happen, nor can it twist. Okay, so if I'm braced only at the ends, I have a very large unbraced length LB, right? In this case, LB would be equal to the span of the beam. That doesn't happen very often. Most likely, beams are going to be braced at locations of concentrated loads because there's something framing into that to provide that concentrated load. Metal deck, when we put the metal deck on top of the beam, that also provides bracing since it's attached to the beam by welding or nails. So unbraced length can vary. We'll start out simply where our unbraced length is very short, and then we'll move on to more advanced where we have longer unbraced lengths. Okay. Certainly chapter F is our primary one, which is flexure, right? So this is moment capacity. Moment strength, I should say. And then shear, right? This is going to be V sub n. Shear strength, this is going to give us our nominal moment capacity. And again, chapter F looks like this. Lots of sections, but we're going to deal primarily with just certainly about this compact eye shapes bent about their major axis. Okay, and non-compact shapes. We won't deal with slender, it just gets a little bit too involved, but compact shapes also. Okay, lots more in here that we won't deal with, but we'll give you a good introduction to it. Okay, again, notice the references down here. There's chapter G is reference for shear. We'll see H when we get into chapter 6, which is combined axial and flexure. Okay, on the page to the right of this page, right, this is 16.1 44 in your steel manual. Okay, the next page over, 16.145, gives you a nice summary of for this type of cross section, what are the potential limit states. Okay, these are the I'm sorry, this is the limit states. This is the flange compact and is the web compact. All right, so again, if you look at this down here, first thing, C is compact or non-compact. Compact is the ideal condition. Okay, that's the best you can hope for. Notice these abbreviations here. Y is for yielding. Okay, LTB, lateral torsional buckling. That's a between those two limit states. We'll deal with that. That will cover most of our discussion. Okay, but we do have to watch for flange local buckling, where the flange would buckle before the entire section. Web local buckling, we'll see, doesn't really happen too often. All right, so we'll deal primarily with this section F2, and we'll dabble in F3 for non-compact flanges only. And again, so we'll touch on yielding, lateral torsional buckling, and flange local buckling. Okay. Oh, been here, done that. Okay, and then chapter G for shear, right? Again, we'll mainly deal with just G1 and G2. Okay, notice this starts to reference chapter J, which is on connections. Okay, pretty much the provision in chapter G that we'll deal with is this one, and you'll see, I'll point out this to you right now. All right, AW, area of the web, which is going to be D times TW. So we'll get to revisit shear stress, which is VQ over IB. But then we also hopefully recall that shear stress for steel beams is we can take shear divided by area of the web, and we're going to see that in action right here. Okay. Again, we will dabble in chapter J for connection type items. All right, so beams, this we would call, right, a wide flange beam. This would be a plate girder or a built up I section. But we will see things like H over TW for our width to thickness checks. Okay, just like we did with columns. Okay, we'll see B sub F. All right, this is the width of the flange, certainly down the middle. This is going to be B sub F over 2. So for a flange, and it has a thickness, T sub F. So we'll also look at B sub F over T sub F. That's another width to thickness ratio that we'll check. Okay, so again, flange, bottom flange, top flange, right? And then this is the web. And think about it back to the columns, stiffen versus unstiffen. Okay, we will discuss that in the next section or so. Okay, so ultimately we get to this. This we're going to get from loading, right? This comes from loading and load combinations. So this is analysis, and this is going to be from, I should really say both of these, all right? Both of these are from the AISC spec. Okay, you can see our our strength reduction factor is still pretty high, 0.9. You can see that our safety factor for ASD is the same, still 1.67, which is also 5/3. Okay, so either our factored maximum moment has to be less than phi m sub n, or our maximum applied moment has to be less than m sub n divided by omega. Okay, so that's going to be flexure. We'll also see for shear, we'll have to have V sub u has to be less than or equal to phi v times Vn, or V applied has to be less than or equal to V sub n over omega V for beams. Okay. But our primary concern is moment. Shear hardly ever concerns, but then there's deflection. So I would say our limit states are our limiting conditions. All right, our limiting conditions are moment first, deflection, and again, this can change depending on span, and then shear. All right, shear hardly ever controls. Sometimes moment controls, sometimes deflection controls. Okay, so we'll get all those as we get through this chapter. All right, so I'll stop here again. Don't hesitate to contact me with questions.